This is the introduction to the inferential statistic. Today we're going to talk about the estimation of the population parameters using some numerical measurements of the samples. We're going to introduce the likelihood functions and also the logarithmic likelihood functions, and also we're going to talk about how to estimate the population's parameter in a best way, for example, in maximizing the likelihood functions. So first of all, let's define what is statistic. Statistic is a numerical measurement obtained from the sample, obtained from the data. So for example, if we collect the data, calculating its mean or the standard deviation is going to be called the statistic or the point statistic. And if we're getting some intervals from the statistic, for example, the x bar plus minus the standard deviation, it's going to be the interval statistic or the range statistic. So please note that every time we're going to get like the new samples, like a statistic of the sample is going to be a random variable. So it's important for our next lecture where we're going to talk about like choosing the intervals and the confidence intervals. Parameter is a numerical measurement of the population. Basically, it's like a mean of the whole population of the country or all the students in the country, all the students in this university, and so on. Or, for example, the average lifetime of all the items which are produced in the factory. So this kind of like this kind of estimate, like numerical measurements, are called the parameters. So let's do just an example in order to understand what is the difference between the statistic and a parameter. So you believe that the lifetime of a certain type of the light bulb followed an exponential distribution with a parameter lambda. So could you please define which of the following numerical measurements is the sample? So the first is the sample's average, x bar. It's basically I'm going to choose some number of the light bulbs and I'm going to measure their lifetimes, and then at the end I would like to find the average lifetime for the sample of the light bulbs. So this is going to be x bar. So the expected value of the sample 1 over lambda, it's basically so in the parameter of the exponential distribution, lambda is the like 1 over lambda is going to be the average lifetime, and the difference between the x bar and 1 over lambda. So from here, the answer, the statistic, is the first numerical measurement, x bar, because it is obtained from the data. So the lambda here is a parameter of the data. So depending on what is the lambda, we can get the different distribution of the lifetime of the items. So the estimation is a procedure by which the information contained within the sample is used to investigate the parameters of the population. So usually in a part of the probability we talked about before, we used to have the parameter, and depending on the parameter, we generated the data. For example, if you know the p, the population of the success, you can generate the sequence of the zeros and ones depending on the p, right? So now the problem is the vice versa. So we obtained the data. For example, after the Bernoulli trial, we've got the sequence of the ones and zeros. And now I would like to know what was the p which has been used in order to generate this data, right? So we would like to estimate the best value of the parameter p. So this parameter might be different depending on the distributions. For example, let's assume we assume that the distribution of the student scores after some exam have the normal distribution, and let's assume we cannot calculate by some reason the population mean, the average score for all the students. But at the same time, I can calculate the samples mean, so x bar, and I would like to say, okay, so you see, so sometimes the samples mean, or most of the time the samples mean is different from the population mean. So what I want is I would like to guess the population mean knowing the samples mean in a best way. So this is called the estimation of the population parameter. So before we start, we're going to define the likelihood functions. So many probability distributions have unknown parameters. We estimate those parameters using the data which you obtained from the sample. So the likelihood function is the probability function which depends on the parameters. It's a tool which summarizes the data using some unknown parameters. So in order to give you what is the likelihood function is exactly, let's consider an example. Let's say we're interested to creating the probability mass function when we flipped a fair coin twice. So the outputs might be the tail and tail, tail and heads, or heads and tail, and heads and heads. The probability mass function here, it's the function which gives us the probability of appearance of the different outputs, right? So here, so if I would draw this, its histogram or the bar chart, it's going to be like the probability of appearance of each of the outputs. While the likelihood function, it gives us the probability of getting the certain output depending on the parameter. So let's flip the coin twice and assume that we've obtained the two heads. We don't know whether this is the fair coin or the biased coin. We don't know what is the probability of obtaining the heads. At the same time, probability that we're going to have the two heads with some p is going to be the p square, right? So the graph of the likelihood function is looking like the parabola. So this gives us the probability of obtaining the t hats for the different values of the p. For p is the probability of obtaining the hats, right? So the probability of obtaining the t hats, where the probability of obtaining hats in a single trial is 0 is 0. And then, for example, the probability of obtaining the t hats, where the probability of obtaining the single hat in a single trial is this value, right? So you see, so it's going to give us the probability, the likelihood function gives us the probability of obtaining the data, the t hats in our case, when we use the different values for the parameter. So for example, let's assume if I would like to flip the coin 3 times, and let's assume I've got the t hats in the first 2 trials and the tails on the third trial. The likelihood function is going to look like this. So the probability to obtain the t hats and the tails exactly in this order is going to be p squared multiplied as 1 minus p, and the likelihood function's graph is looked like this. So here this graph represents the probability of obtaining the t hats and tails in a row for the different values of the p. So by putting the different values of the p, we can get the different values for the probability of obtaining exactly this data. So the likelihood functions are very similar, so they might look like similar to the density functions, but fundamentally they are different. While the probability density function, it's a function which gives us the probability of appearance of the different outputs. The likelihood function, it gives us the probability that appearance of the data under different parameters. Okay, so let's consider another more realistic example of the likelihood functions for the binomial distribution. Suppose we would like to know the percentage p of people in a whole country who knows what is a Twitter. So obviously I cannot ask all the people in the country and know what is the percentage, exact percentage of the people who know what is a Twitter. So what I can do is I can ask n people, and my data points, they are going to be the answer from each person, and it's going to be to have the Bernoulli trial. So I'm going to collect the answers yes or no, and I'm going to denote as a 1 and 0, right? And the data is going to be 1 and 0 depending on some parameter p. So this p is the population's proportion who knows what is a Twitter. So I would like to estimate this. I would like to know what is this p. So the results after the experiment, I'm going to get the x1, x2, and so on, xn are the answers of the people. So they are going to take the values either 1, either 0. So I would like to estimate this p from the sample. So let's assume I ask 100 people and 55 say yes, they are familiar with the Twitter. So I would like to use this data in order to estimate the P, the percentage of the people in a whole country who knows what is a Twitter. So before we start, we're going to uh, create the likelihood function here. So the likelihood function, it's the probability of obtaining 55 successful trials, basically 55 ones in my data out of the 100 trials for some P. Okay, so which I don't know what is this. So since we have the binomial distribution, the number of the successful trials has the binomial distribution, or the number of the people who said yes, they know what is a Twitter has the binomial distribution. I can evaluate the probability using this formula. So the combination of the 155, p in the power of 55 multiplied to the q, which is 1 minus p in the power of 45. So this is the likelihood function for a given data for the unknown p. So in order to choose the estimate, the parameter p, I would like to choose the estimate by maximizing the likelihood function. So the maximum likelihood estimate is evaluated p that maximizes the likelihood function. So usually I'm going to maximize the likelihood function by taking the derivative with respect to the p and equalizing this to the 0. So sometimes if the derivative is never be equal to the 0, I would like to maximize the likelihood function at the ending points of the allowable range for the parameters. So let's maximize the likelihood function for our experiment. So the likelihood function is given like this. So I would like to take the derivative of this function with respect to the p and equalize this to the 0 in order to maximize this. So the derivative is going to be, so I'm going to use the multiplication rule for taking the derivative. It's going to be derivative of the first part, which is 55 multiplied to the p in the power of 54, plus the derivative of the second part, which is 45 multiplied to the 1 minus p in the power of 44, multiplied to the minus 1, which is the derivative of the 1 minus p according to the chain rule. So if I equalize this to the 0 and simplify this and using the algebraic operations, I can obtain that the p is equal to the 55 over 100. So this is the maximum likelihood estimate. So I obtained the p, which is going to maximize my likelihood function. So sometimes it is better for us it is more comfortable for us to use the logarithmic likelihood functions, because the logarithmic functions turns the multiplication into the addition, and also it has like a good property that the ln of the x in some power of the p is going to be p multiplied to the ln of x. And since the natural logarithm is monotonic, maximizing the likelihood function is equivalent to the maximizing the logarithmic likelihood function. So let's define the logarithmic likelihood to our experiment. So do you remember that the likelihood function for our experiment was like this, and the logarithmic likelihood function is going to be the ln of the first part, right? So because the logarithm of the multiplication of the 3 part is going to give us the logarithm of each part and then the addition, right? So please note the first term is going to be constant here. So if I would like to maximize this logarithmic likelihood function, I'm going to take the derivative of this with respect to the p, and I'm going to equalize this to 0. So derivative of this function is going to be, so this is the 0 because this is just a constant. Derivative of the second term is going to be 55 multiplied to 1 over p, and derivative of this one is going to be 45 multiplied to the 1 over 1 minus p, multiplied to the derivative of the 1 minus p, which is minus 1, right? If I equalize this to the 0, I can find a p is equal to the 55 over 100. So in this case, for example, it was slightly easier to get this maximum likelihood estimate. So now let's do an experiment in order to get intuition why we have to maximize the likelihood function. So let's assume I've got 3 coins on a bucket, and so 2 of them are the prize coin and 1 of them is a fear coin. Basically, the probability of obtaining the heads for the first coin is 1 over 3, for the second one is 1 over 2, for the third one is 2 over 3. So let's assume I choose one of the coins and toss this 80 times, and I've got 49 heads and 31 tails. I just would like to know what which kind I've chosen. So in order to do this, so first of all, let's calculate the likelihood function for each of the kinds. Then let's estimate the parameter, the probability of the getting the hats for this kind using the maximum likelihood estimate. So the likelihood function for the first kind is going to be basically the probability of obtaining 49 hats using the first kind is equal to this one, which is equal to the very small number. The probability of obtaining 49 hats for the second kind is going to be 0.024, and probability of obtaining the 49 hats for the third kind is going to be this number, so which is like the biggest, right? So it says us that we use the third kind for obtaining 49 hats. You see, so the likelihood function is maximum on a p, on a value of the p of the population. So let's now try to maximize the likelihood estimate. So if I would not know what is the p, the likelihood function would be like this. I would like to maximize this and find a value of the p which will maximize this. So in order to do this, I'm going to first of all define the logarithmic likelihood, and by taking its derivative with respect to the t and equalizing this to the 0, I can find that the p is equal to the 49 over 80, which is equal to 0.60t roughly, so which is very close to the t over 3, right? So our estimate is going to be 0.60t, and actual parameter was actually 2.3, right? So the maximizing the likelihood function gives us the best guess. So when we are going to define the likelihood functions for the continuous case, we're just going to define the probability density function just instead of the probability mass function. Let's illustrate this in the example. So let's say the lifetime of the light bulbs has the exponential distribution with some parameter lambda. We're going to choose 5 light bulbs, and we would like to estimate or find the lifetime for each of them. So basically, I just would like to buy 5 light bulbs, and I would like to install them somewhere and just like measure the lifetimes. And at the end, I would like to calculate. So now I would like to define the likelihood function and the logarithmic likelihood function, and then by maximizing the logarithmic likelihood function, I would like to estimate what is the lambda, the average lifetime for all the light bulbs which are produced in a whole factory. So let's say xi is the random variable which gives us the lifetime of the ice bulb. Okay, so for example, x1 has the exponential distribution with a parameter lambda, and this is the lifetime for the first light bulb. So let's assume I calculated this, and the lifetime for the first first light bulb has the value x1, and the density function of the xi is going to be lambda multiplied to the e in the power of minus lambda xi, basically the density function of the exponential distribution. And then we're going to define a joint probability density function by just multiplying the marginal density functions for each of the light bulbs, since we assume that the lifetime of each of the bulbs do not depend to each other. Okay, so by defining this, we're going to obtain the joint density function for some parameter lambda, and this is going to be our likelihood function. So the logarithmic likelihood function in this case would be just like I would like to take the logarithm, and I would like to multiply this multiplication as a summation, and the ln of the L in the power lambda in the power of 5 is going to be 5 multiplied as the ln of lambda, and ln of the e in the power of this big number is going to be minus the power of the e multiplied as the ln of e, which is 1. So now I would like to estimate what is the lambda. In order to do this, I'm going to take the derivative from the logarithmic likelihood function and equalize this to the 0. So the derivative of the logarithmic likelihood function with respect to the lambda is going to be 5 multiplied as a 1 over lambda, and derivative of the second term with respect to the lambda will be just the constant in front of the lambda, right? So this is going to be a 5 over lambda minus the summation of all the x's, and the lambda, our best estimate, our maximum likelihood estimate is going to be 5 over xi. So for example, suppose that the 5 light bulbs are tested and have the lifetimes 2 years, 3 years, 1 year, 3 years, and 4 years. Just using this samples data, I would like to know what is the estimate or what is the average lifetime for all the batteries in this store, right? So if I just put this everything here, it's going to be 5 over 13, and we know that the average lifetime for the exponential distribution is going to be 1 over lambda, right? So the average lifetime for all the batteries is going to be 13 over 5 years, so which is equal to 2.6 years.